Hello, this is Yim from Seoul National University. Today, we are going to talk about topology optimization of planar gear linkage mechanisms. This video explains how to synthesize the mechanism to create the desired path to consider with respect to gear, components, and link components. This study was also published in Journal of Mechanical Design in 2019. For more information, I recommend you to read the paper written below. As the industry develops, we need more creative and more complex mechanisms. We want to synthesize a 1 degree of freedom mechanism that follows the target path without having any design baseline for creative and complex results. Suppose you do not know the baseline of the mechanism. How do you know the type of mechanisms, such as a linkage-only mechanism or a kinematically different type of gear linkage mechanism? Therefore, our goal is to propose a unified method that can synthesize different types of mechanisms without baseline design. There are several issues to solve this problem. One is a baseline-free synthesis method, and the other is a unified geared and gearless mechanism synthesis method. As I mentioned in the previous slide, there are two issues to solve this problem. First, how to synthesize a new mechanism without baseline design. You can use mechanism topology optimization to perform number and dimension synthesis simultaneously without having information on the baseline design. For more information on how to synthesize the mechanism with topology optimization, we recommend that you retrieve the keywords of SBM and work transmittance efficiency. Second, how to synthesize gear linkage and gearless mechanisms within a single unified formulation. Considering different types of mechanisms requires new ideas to modeling various components simultaneously. This is because previous topology optimization cannot handle mechanism type synthesis. Then, what is the mechanism synthesis by topology optimization? Let's think about this. We have an input motion from the input motor. We want to synthesize a linkage-only mechanism that follows the target path on a particular end effector. Let's see the example of mechanism synthesis by topology optimization. As you can see, this mechanism synthesis method does not require a baseline of mechanism. Because no reference mechanisms are required during mechanism synthesis, the method can produce results beyond the designer's experience and provide researchers with creative institutions. The process of linkage-only mechanism synthesis by topology optimization is as below. First, there is a black box design domain with a target path and input motion. We want to synthesize 1 degree of freedom linkage-only mechanism along the target path in the end effector. Second, we discretize the design domain with linkage design space, which consists of rigid blocks. As you can see in the link design space, all rigid blocks are connected by zero-length translational springs. The final step is to optimize the stiffness of each spring. Let's see more detail about this modeling. Modeling named the spring block model discretizes design domain by rigid blocks and zero-length translational springs. The combination's stiffness of spring can represent different kinds of links and joints. As seen in previous works, many mechanism syntheses by topology optimization researches have been studied. However, they only consider the linkage type mechanism. So there is no way to synthesize a kinematically different type of gear and link mechanisms. To model a gear as a component, a new idea is needed, that is gear block. What is a gear block? Literally, the block acts as a gear component, which we called a gear block. The rotation angle of the gear block has a particular relationship with an input block. If the ratio of gear block is 1, when the input block rotates theta, gear block rotates minus theta. With using this relation between input block and gear block, we can define all kinds of gear ratio gear blocks. Furthermore, all gear blocks rotate regardless of the other gear. blocks and rigid blocks. They rotate as background. Two things must be considered at the same time to model gear components. One is the existence of gear components, and the other is the gear ratio. In topology optimization, using extra heterogeneous variables increases the difficulty of an optimization problem. That is the reason the previous study cannot synthesize a different type of mechanism. So in this study, we focus on modeling not to use extra heterogeneous variables. Earlier, the SBM modeled a linkage mechanism using rigid blocks and translational springs. We use a gear block and 4 translational springs to represent the existence and non-existence of gear components. The gear components have a particular relationship with an input motor angle so that the gear elements can be modeled with one torsional spring. However, the dimensions of the torsional spring and the translational spring are different. To avoid using other heterogeneous variables, we model the presence of gears using 4 translational springs rather than one torsional spring. And it is the same to gear ratio. In representing the gear ratio, we define different gear blocks with varying gear ratios without using shape variables and model them by overlapping each other. Therefore, this modeling uses only translational springs to model the existence of gear elements and gear ratios. That is the crucial point of this research. Let's see the difference between the previous SBM and the newly proposed model. Previous SBM modeling discretizes the design domain with only linkage design space. And linkage design space consists of rigid blocks and zero-length springs, so SBM model can only synthesize dimension and number of linkage mechanisms. But the newly proposed model, we also discretize the design domain with gear design space. The gear design space consists of gear blocks, each of which rotates regardless of the other blocks, and overlap gear design spaces with linkage design spaces. And if you want more various gear ratios, you can overlap other gear design spaces together, and each gear block is connected with a rigid block with 4 gearing springs, which are zero-length translational springs. Stiffness of gearing springs represents the existence and non-existence of gear elements. Then, how the newly proposed model can model the gear mechanism. As you know, the gear block is connected by a rigid block with 4 gearing springs. If the gear springs have a minimum stiffness value, this indicates that the gear is disconnected. As you can see in the video, the rigid block, which is a green block, moves regardless of the blue gear block. The red line is an extended gearing spring, but it does not affect the rigid block due to the minimum spring stiffness. If the stiffness of the gearing spring is between the minimum and maximum values, this means that the status of modeling is not a mechanism. But as you can see, the movement of the rigid block moves slightly along the gear block, but it is not a mechanism. Finally, the gear component is synthesized when the gearing springs have a maximum stiffness value. As you can see in the video, the rigid block moves exactly the same as the gear block. That is, the gear element is synthesized. Therefore, when the mechanism is synthesized, all spring stiffness must be a minimum or maximum value, not a value between 2 of each. Formulating the correct optimization problem is essential to make spring stiffness a minimum or maximum value. To formulate a topology optimization problem, we use energy transmittance efficiency as an objective function and Euclidean error as a constraint function. If the energy transmittance efficiency approaches 1, the system becomes 1. If you want to know more about energy transmittance efficiency, see the reference paper below. For detailed formulas for optimization, we recommend that you view the paper of this study. We then prepare several case studies to validate the proposed method. We use a 3x3 discretized design domain in all case studies, and we use 1 gear ratio gear design space and 2 gear ratio gear design space. The optimization conditions are as follows. There is a target mechanism consisting of geared 5-bar linkage mechanism with 1 gear ratio. We are trying to validate a new method using the target path from the known target mechanism. Let's synthesize the mechanism. First, place 1 gear ratio design space. Because the correct gear ratio is not known until the mechanism is synthesized, 2 gear ratio design spaces are stacked with 1 gear ratio design space and overlap 2 gear ratio gear design spaces with linkage design space. As you can see, all the gear spaces are connected by rigid blocks with gearing springs. As the iteration passed, you can see the gear shape on the right side of the video. Large gear shape means 1 gear ratio, and small gear shape means 2 gear ratios, and thickness means stiffness of the corresponding gear spring. As you can see, the gear element is synthesized on the third block. When the iteration passed, the gearing spring value of the third block means that it has maximum stiffness, that is, 1 gear ratio. Third gear block is activated. As you can see, the exact mechanism is synthesized as target mechanics, which generate the target path. The second case study is that all conditions are the same as case study 1, and only the target path of the target mechanism is different. As the iteration passed, a gear block with a 2 gear ratio is synthesized. Thus, using two case studies, the proposed method can synthesize gears and linkage mechanisms with different gear ratios. And I brought some other more case studies. 3 case studies have the same conditions as case studies 1 and 2. As you can see, with the same modeling, it is possible to synthesize different types of mechanisms, such as linkage-only mechanism, 1 pair of gear linkage mechanism, and 2 pairs of mechanism. So, various types of mechanisms can be synthesized by the newly proposed method. As you can see in the iteration history, the work transmittance efficiency approach for 1 means that 1 degree of freedom mechanism is synthesized. Euclidean error tells synthesized mechanism to follow the target well. As a result, this is the first time that gear and link components have been integrated through topology optimization in a single method. It means we can synthesize the type, number, and dimension of the mechanism simultaneously. Thank you for listening my presentation. I hope you enjoy my presentation.